Hi, welcome to lesson 5.1, Angles of Triangles. Now, before we begin, please make sure that you tear out the following pages in your Chapter 5 student journal, pages 123 to 158. Now, for the sake of this chapter, we will not be covering lesson 5.8, so you can either leave it in your book or toss it out. Pause the video and restart the video whenever you are ready. Now for this lesson, the materials that you are going to need is a quarter of a sheet of paper. So what you need to do is once you have a half sheet of paper, simply cut it in half and you will get a quarter of a piece of paper. For example, here's a half sheet. Simply fold it in half and cut it. Okay, so place that piece of paper right on top of page 123, covering up all the material that is under here that we are not going to need. And we're going to use this piece of the first exploration to go over two of the main topics for this lesson. Now on page 124, you are going to need a half sheet of paper and you are going to glue for problem number 2, and this goes on page 124. Now on page 125, you are going to put number 1 here and example number 3 right there, and we'll go over all these things in just a bit. Now on the next page, page 126, you are going to be doing a proof. Actually, we're going to be doing a proof right here and example 4 down here on page 126, and we'll cover all these in just a second. Okay, so pause the video, go ahead and get your notes ready, and then start the video once you're ready for the exploration. So let's go back to page 123 and let's talk about what we have here. Now today's lesson has everything to do with the angles of a triangle. This is in preparation for chapter 5, which deals with triangle congruence. Now, what you have here in this triangle is a triangle here where they actually give you all 3 of the measurements of that triangle. So part of our prior knowledge is that the sum of the angles is going to be 180. So what we're going to do is we're going to add all of these measurements and see if that's going to be true. So using my calculator, I'm going to type in 43.67 plus 81.87 plus 54.46. Press equal, and you notice that that is indeed 180 degrees. So what is going to be our conjecture? Our conjecture is going to be that the sum of the angles in any triangle is going to be 180. And in the proof that's going to happen on page, I believe, 125, we are going to prove why is it that it's 180 degrees. So our conjecture is that the sum of the angles in a triangle is 180 degrees. Nothing new, but what we're going to do is we are actually going to prove this. Now, taking this a little bit of a step further, I want to investigate something. If I were to draw a ray from B to C, like this, from B to C, and make an extension like this, okay, we get a whole new angle created here, okay? The angle that I'm talking about is this angle here. Now, that angle, in order for me to call it anything, I have to put a point somewhere on here, and I'm going to call this point D. So we're going to use the top piece of paper to write our part of the notes. So my question is, what is equal to what's going to be the measurement of angle ACD? That's our question. Now, I can easily figure out how much it's going to be because I do know what angle C is. Now, angle ACB is the same as angle C in the original diagram. So what we do know is that the measure of angle ACD plus the measure of angle ACB, I know that is 180 degrees because it is indeed a linear pair. Now, angle ACB, that's the same as this one. So we already know what that is. What we're going to do is we're going to substitute that value in here and figure out what this is going to be. So the measure of angle ACD plus ACB, which is 54.46, ACB, 54.46 is equal to 180 degrees. Now what we're going to do is we're going to subtract 54.46 from both sides of the equation. So the measure of angle ACD is equal to, now I'm going to put my calculator here so you can see, 180 minus 54.46. And that's going to be 125.54. Now, this is what that angle is going to be, 125.54. So let's look at that. Now, I want to focus on something right now. Is there a relationship between these two angles right here and this angle right there? Well, let's take a look at these two. What would happen if I were to add those two? So the measure of angle A plus the measure of angle B. What would that equal? So I do know what those measurements are. Those measurements are 43.67 and 81.87. So what happens if I add those two? 43.67, whoops, clear that. 43.67 plus 81.87, you ready? Equals 125.54. Very interesting. Isn't that the same thing as this? It sure is. So what does that mean? It means that the sum of the two interior angles, called remote interior angles, is equal to the exterior angles. And I'll talk about the vocabulary in just a second. So what I'm trying to say here is, well, I can use that color. Let me see if I can have another color here. Oh, I got purple. Okay, so this angle right here plus this angle right there is going to equal this angle right here. Okay, so a little bit of vocabulary, or actually we can just go to our next conjecture. Our conjecture is this: the sum of the remote, or they also call them non-adjacent interior angles, so whichever one works best for you. Oh, let me raise it up. Okay, the sum of the remote interior angles is equal, it's equal to the exterior angle. In other words, this angle plus this angle, which is a non-adjacent angle to this angle, is equal to the exterior angle. Very simple. This plus this equals this. And that's, I mean, we haven't done a proof, but we're going to do a different type of proof in a bit. All right, so this is on page 123. Let's go really quickly to page 125. And let's go over a little bit of very, very important vocabulary that you need to know. This is actually prior knowledge, but it's good to do a little bit of review. So what we're going to do is we're going to classify a triangle using two methods. The first one is by the sides, and the second one is by the angles. Now, when you have a triangle that has a completely different set of sides, meaning that no sides are the same, we call that a scalene triangle, where no sides happen to be congruent. Scalene triangle. If you have at least two sides that are congruent, then we call that an isosceles triangle. And if all three sides are congruent, we call that an equilateral triangle. So these are the three types of triangles that you have if you want to classify them by the sides. If you want to classify them by the angles, there are four different types of classifications that you could use. So the first one is called an acute triangle. This is if all the angles of the triangle are acute, meaning that they are all less than 90 degrees. So if you have three acute angles, we call it an acute triangle. If you have even one angle that is a right angle, we call it a right triangle. And if you have one angle that has at least one obtuse angle, meaning more than 90, less than 180, we call that an obtuse triangle. Now, when all the angles are the same, okay, this is kind of like a special classification. When all the angles are the same, it is considered to be an acute triangle and an equiangular triangle, which also happens to be an equilateral triangle. We're going to look at a proof of that later on, perhaps not this lesson, but in the next couple of lessons. Okay, turn the page to page 126. Now, these are the three theorems that we are going to cover. Okay, the first theorem is called the triangle sum theorem. It says the sum of the measures of the interior angles of a triangle is 180 degrees, meaning A, B, and C, the angle measurements add up to 180 degrees. We're going to do a proof on that in just a bit. The exterior angle theorem says that the measure of the exterior angle of a triangle, meaning this one, is equal to the sum of the measures of the two non-adjacent interior angles. Here's the key word, non-adjacent interior angles, meaning angle A and angle B. And we already saw an example of how that worked. Now, a corollary, probably you haven't heard the word corollary yet. A corollary is kind of like the cousin of a theorem. It's related to a major theorem, but it's kind of like a subset of a theorem. So this is a corollary to the top one right here. And it says this: the acute angles of a right triangle are complementary. And it makes sense because if all of these add up to 180, and this one here is a right angle, that means that this is 90. If you subtract that from 180, that only leaves these two to have a sum of 90 degrees, making them complementary. Okay. Now what we're going to do is we're going to prove the triangle sum theorem. Okay, so in order to prove it, we're going to look into using the same diagram that we have right now. So I'm going to zoom it in a little bit more so you can see what we're going to do. Okay, so what I'm going to do is I am going to number these angles rather than using the letters because it's going to be very less confusing. So the way that I'm going to number these are like this: 1, 2, and 3. Paper's ripping. Okay, so 1, 2, and 3. Now here's what we're going to do. Okay, there was a theorem, I know we don't use it very often, called the parallel postulate, which states that there exists only one line parallel to line AC going through B. So what we're going to do is we're going to draw a line, draw a better line, okay, draw a line that is parallel to AC. Okay, so that means that this line here is going to be parallel to that line right there. Now, since I did that, I actually have created two more angles that I'm going to call angle 4 and angle 5. Now, there are a couple of things that we do need to go back and remember. Okay, if you have a set of lines like this one and this one cut by a transversal, then you're going to have a couple of angles that are going to be congruent. Okay, so the first ones that are going to be congruent are 1 and 4. I don't know if you can see it in the yellow there, but those are going to be congruent because of alternate interior angles. Now, the other two that are going to be congruent are 2 and 5. Those are going to be congruent by alternate interior angles. So we're going to use this in order to show that the sum of these three right here is 180 degrees, and therefore using some substitution and showing that the sum of 1, 2, and 3 is 180 degrees. So here's what we need to prove. Okay, we need to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. That's what we need to prove. Move to the side a little bit. Okay, so that's our goal. And we have almost enough space to do it on this, so try to write small so you can fit everything in there. All right, so what we're going to do is we are going to set up our two columns. Okay, so our first step is going to be, let's see if I can fit it all in here. Okay, so what we did is we did line BD. Well, I didn't put the D, so you can put a D right there. Okay, line BD parallel to line AC. That's what we did. And this is called the parallel postulate. Okay, the second thing. Now, based on the fact that 4, 3, and 5 all form a linear pair, not a linear pair, but like their sum is technically 180 degrees because it does make a line. So the measure of angle 4 plus the measure of angle 3 plus the measure of angle 5 equals 180 degrees. And this is just because of the definition of a straight line. Definition of a straight line. Now for number 3, we're going to have to state that there is a relationship between angle 1 and angle 4 and angle 2 and angle 5. Now this is from chapter 3. Okay, these angles right here are alternate interior angles. So alternate interior angles theorem states that these are going to be congruent. Now, because they are congruent, their measurements are going to be the same. So the measure of angle 1 equals the measure of angle 4. The measure of angle 2 equals the measure of angle 5. And this is simply because of the definition of congruent angles. Now, the reason why we did that is because now what we're going to do is we are going to substitute here and here. So instead of the measure of angle 4, we're going to write the measure of angle 1. The measure of angle 3 stays the same. And the measure of angle 2 is going to be replaced with the measure of angle 5. Oh, no, measure of angle 5 with angle 2. Now, even though these are out of order, it's technically the same thing. Okay, what we did was a substitution. Hence, now I have proven that the sum of the angles of the interior of a triangle is 180 degrees. Now what we're going to do is we're going to proceed to the examples. So let's take a look at example number 1. Now remember, pause the video and write down the problem and then proceed to unpausing the video whenever you're ready. Now this diagram is a little hard to see, but what you see in here is a triangle with a set of congruent sides. So if I were to recopy this, it would look something like this. Now when you're copying these guys, you don't really need to copy everything else that's in it, just the important information. So it says classify the triangular shape of the support beams in the diagram by its sides and by measuring its angles. So if we just look at the sides, you notice that there are two sides that are congruent. So based on our definitions that are on page 125, this is going to be an isosceles triangle. Now, if I were to measure it, you would notice that all these angles are strictly under 90 degrees, which makes this also an acute triangle. So if I were to classify this, I could call this an isosceles acute triangle, or acute isosceles triangle. It doesn't really matter which one goes first. So how do I know it's isosceles? Because it has two congruent sides. How do I know it's acute? Because all these angles are strictly less than 90 degrees. I could grab a protractor and measure them if I wanted to. So that is example number 1. Let's look at the next example. Now, this example is a little bit more involved because what they want us to do is they want us to classify the triangle by its sides and then determine whether it's a right triangle or not. So what we need to do is the distance formula for every one of those sides. And with that, we're going to be able to figure out if this is going to be a a scalene, isosceles, or an equilateral. Obviously, it's not going to be an equilateral. You can see that, but we got to discard the reason why it is that. So here's the thing. We need to figure out the distance for all three of the sides. So I need to figure out the distance of OP. I need to figure out the distance of PQ, and I need to figure out the distance of OQ. And for that, we are going to have to use the distance formula. So if you don't recall the distance formula, it's going to look something like this. It's nothing new. We have done this before. That's the distance formula. Okay, so what we're going to do is we're going to use that in order to figure out the distances. So let's start with OP. Okay, so O and P. I'm going to use those two coordinates. I always like to set these up like this so that I don't forget any step. So it doesn't matter which one you make your X1 and your X2. I always like to go from top to bottom. Whatever you choose to do. So let's do the differences of the x's. -1 minus 0. -1 minus 0. Differences of the y's. 2 minus 0. Now go ahead and simplify. -1 minus 0, that's simply -1. 2 minus 0, that's simply 2. And when I continue simplifying this, this is going to give me 1, and this is going to give me 4. So this is going to give me the square root of 5. And you honestly do not have to put it in a calculator. Just leave it as is. So that is the distance of OP. The next one I'm going to do is the distance of OQ. So it's the same process. Whoops. I already know the equation. I don't need to do that. Okay, so once again, top to bottom. Okay, so 6 minus 0, 3 minus 0. And that's going to be easy because that's 6 squared plus 3 squared, which is going to give me 36 plus 9. And that's going to give me the square root of 45. Okay. So as you can see, OQ is the square root of 45. The only thing that's left to do is find the distance of PQ. So for PQ, I'm going to do exactly the same thing. Yes, it is a lot of work. Okay, so for PQ, I always like to do top to bottom. So 6 minus negative 1. Here's where people make mistakes. Don't make that mistake. Make sure you include the sign in there. 6 minus negative 1 and 3. Give me 1 second. Having technical difficulties here. That's why I hate mechanical pencils. Come on. Okay, I guess I have to switch pencils now. I have to find one that has pencils. I'll switch to pen. How's that? Okay, so 3 minus 2. Hopefully I won't make a mistake. Okay, 3 minus 2. This is going to turn to addition. That's going to be 7 square. That's going to be 1 square, which is going to give me 49 plus 1, which is the square root of 50. So PQ is the square root of 50. So as you can see, all three of these are different. Okay, so if all of these here are different, then we are going to have a scalene triangle. Now the question is this going to be a right triangle or not? Now there's different ways to do this, but the easiest way is by using the slope. So I would have to look for the slope of PO, OP, same thing, okay? And I would have to look for the slope of OQ and see if their product is indeed going to be -1. So looking at the graph, you can see here that the slope here is going to be, the rise is 2, the run is 1, and it's a negative. So that's going to be a -2/1. And the slope of this one is going to be 3/6. So if I were to multiply those two, I'm going to get -6/6, which indeed is going to give me a -1, which means that the angle is going to be a perpendicular. Now, what does that mean? That means that this is going to be a right triangle as well. If this is not -1, then it is not a right triangle. And that is example number 1. 2, not 1. All right, let's look at the next example. The next example is a very, very simple application. So one of the theorems that we did learn was the exterior angle theorem that stated that the two non-adjacent angles, their sum, is going to equal the exterior angle. So these two angles right here, these are the non-adjacent interior angles. Okay? So I have to add those two, and I have to equal it to this angle, which is the exterior angle. So I'm going to add them. X plus 70 equals the exterior angle, which is 2x minus 5. Now your goal is to solve for x. Subtract x from both ends. You get 70 equal to x minus 5. And you add 5 to both sides. And you get 75 equal to x. Now that's not your answer because the question is asking for JKM. So that means you have to go back and plug it in into 2x minus 5. So the measure of JKM is going to be 2 times 75 minus 5. That's going to give you 150 minus 5, which is 145. So that's the measure of JKM. Always read the question. Because a lot of people get to this answer, they solve for x and they think they're done. But if the question is not asking for x, it's asking for an angle, you have to solve for x and then go back and plug it in. So always pay attention to the problem. All right, let's take a look at the next one. It says, in the painting, the red triangle is a right triangle. Okay, this one right here. I know it's kind of hard to see it, but it's that one. Okay. The measure of one acute angle in the triangle is twice the measure of the other one. So if I were to focus only on that right triangle, it tells you that one angle is twice the measure of the other. So if this angle, for example, here is x, and the other one is twice the measurement of this one, twice the measurement of x is 2x. Now, the theorem that we did learn, corollary 5.1, the corollary to the triangle sum theorem, says that these two angles, the acute angles, their sum is going to be complementary. So that means x plus 2x equals 90, giving you 3x equal to 90, divided by 3, x is going to equal 30. So find the measure of each acute angle. You know one of them is 30, so the other one is twice of that, so 2 times 30 is 60. So that is going to be the angle measurements of those. And that brings to the end lesson 5.1. Okay, make sure you guys are working on your extra practices. Have a great day.